Assalamualaikum and hi to everyone. Thank you for watching this video. So in this video, we continue on another chapter, visual memory. So in the previous chapter, we already learned about the main memory. So basically, you should know the process, what happened in the main memory, the memory management units, the responsibility, the rules, okay, and the function of the MMU. And then you already know about the binding address, how the process of mapping the logical address to the physical address. So in this new chapter, we will learn about the virtual memory. So basically, it is a memory, but it like a visual machine. Okay, it's not physically there, but is idealistic. Okay, the idea it is there, but actually it's not there. Okay, something like that. So in this chapter, we'll cover on the background part and the page fall. What is the page fall? Okay, we have the paging inside the table, and what is the page fall, and then the demand paging, and then we will learn about the page replacement, allocation of frame, and tracing. So the first part we learn the first three, and then we continue another part with the page replacement, allocation of frames, and tracing. So objective for this chapter, okay, at the end you should be able to describe the benefit of a visual memory system. Next, you should be able to explain the concept of demand paging, page replacement algorithm, and allocation of page frames. Okay, so it's once again we have the algorithm to go through, and then the third, you should be able to discuss the principle of the working set model. Number 4, to examine the relationship between shared memory and the memory map file, and then to explore how the kernel memory is managed. Okay, virtual memory is a memory management technique that provides an idealized abstraction of the storage resources that are actually available on a given machine. So this is the key of visual memory, means to provide the idealized abstraction. Okay, so this part create the illusion to the users of a very large memory. So we just think that we have a big or large storage, but actually in the physical part there is no that size of the storage. It's just like when we install the visual machine in our PC. Actually we only have one PC, but because we have the visual machine, so it look like that we have more than one PC. We can run it in the same time. So little bit about the background of this visual memory. So code needs to be in memory before it can be executed. So any programming that you wrote, okay, and it's become a program, and they must have a memory space for that code in order to run or execute it. Okay, but entire program really use error code, unusual routine, large data structure. Okay, that's why when you learn about the programming and problem solve part, problem solving subject or course, you need to write the code in the right way in order to save the memory of our computer. Okay, entire program code not needed at the same time. Okay, some program needs, but not the entire program. Okay, consider ability to execute partially loaded program. So program no longer constrained by limit of the physical memory. So each program takes less memory while running, and more program run at the same time. At this part, it will increase the CPU utilization and throughout with no increase in response time and turnaround time. So this a term of response time and turnaround time, we already met this kind of form in the previous chapter. Okay, when less input and output needed to load or swap the program into the memory, so more each user program run faster. So the program can run faster because less input and output needed to load from memory to the from the program to the memory, and then from the memory to another program. Okay, so the next part is about the visual memory. So visual memory is separation of the user logical memory from the physical memory. So only part of the program need to be in the memory for the executions. Second, logical address space can therefore be much larger than the physical address space. So let's say in your machine you only have 8 gigabyte. So using the visual memory, we can have 64 megabyte or gigabyte. Okay, and then allow the address spaces to be shared by the several processes and allow for more efficient process creation, more program running concurrently in your system because you have bigger memory and less input and output needed to load or swap processes from the secondary memory. Visual address space. Okay, when we talk about address space, that means about the size. So logical view of how process is stored in the memory. So usually it start at address 0 and contiguous addresses until end of space. Okay, if you remember about the fragmentation, okay, the address in the computer memory is contiguous, means after 0, 1 and then 2, and it must be continuous. So usually in the memory it will start at 0 address. It's just like when you do programming, when we want to store data in an array, so it starts with index 0. Okay, next, physical memory organized in the page frames and MU must map the logical to the physical logical address to the physical address. Virtual memory can be implemented via the demand paging and demand segmentation. So hopefully you still remember about the paging and the segmentation that we have learned in the previous video. So VM is larger than the physical memory. So as I mentioned before, let's say in the physical we have only 8 gigabit. So in the visual memory we can have more than that. So basically in this diagram we have the visual memory. So it starts with the 0 and contiguous until page N or V here. And then from this visual memory, it will map to the memory map. So memory map will map to the physical memory. Okay, and then here is the process of swap in and swap out. Okay, visual address spaces. Okay, we have starting at 0. So starting usually at the bottom and it goes up. And then in this part, it have several parts: stack, heap, data, and code. So usually design the logical address space for the stack to start at the max logical address and grow down while heap grows up. So stack grow down, stack grow down, heap grow up. So maximize the address space use. Okay, this process when we go down and go up, so we try to maximize the address space. Unused address space between the two is whole and no physical memory needed until heap or stack grows to a given new page. And then enable the sparse address spaces with whole left for the growth, dynamically link libraries, and etc. System library shared via mapping into the visual address space and shared memory by mapping pages read write into visual address space. Pages also can be shared during the fork. Okay, the process of fork is just like parent and children when you learn about the programming. So speeding the process creation. So using this function, it can speed up the process of creation. Okay, this one is shared library using the visual virtual memory. Okay, this one is stack, this one is the shared library, this one is heap, data encode, similar like the previous diagram. And then you can look from stack to the bottom, from heap goes to the up. And then at here we have the shared library. Okay, next is about the demand paging. So in demand paging, it could bring entire process into memory at load time, or bring a page into the memory only when it is needed. So less input output needed, no unnecessary input output that interferes, that interrupt the process. Less memory needed. When the process of we can reduce the process of loading data from input and output, we can reduce the memory use of the computer memory. And then faster response and more users. Similar to paging system with swapping. Okay, this one with swap in and swap out. So page is needed to become as a reference to it. Invalid reference will abort the process, and not in the memory will bring to the memory. Lazy swapper refer to the never swap a page into memory unless the page will be needed. So the swapper that deals with the pages is we call pager. So we have pager, we have swapper. So this one is process of swapping, swap in to the memory and swap out to the secondary disk. Okay, the basic concept with swapping pager gas, which pages will be used before swapping out again. So instead, pager bring it only those pages into the memory. And how to determine the set of pages? We use the MMU. So the needs of new MMU functionality to be implemented on the demand paging. If the pages needed are already a memory resident, so no different from non-demand paging. And if page needed and not memory resident, so it will identify type of the memory, either it's resident or not memory resident. So it needs to detect and load the page into memory from the storage without changing the program behavior and without the programmer needing to change the code. It detects automatically. So it's based on the memory resident or not memory resident. If memory resident, so no different from the non-demand paging. If page needed and not memory resident, so detect and load the page into the memory from the storage. So we can have the valid and invalid bits. So with each page table entry, a valid invalid bit is associated. Okay, we have V in the memory resident, I not in memory. So V refer to memory resident, I refer to not in memory. So initially, valid invalid bit is set to I on all entries. Okay, example of a page table snapshot. So this part is the page table. So in the page table, we have the frame and we have the bit that give a status valid and invalid. I mean not invalid. V means valid. I invalid, V valid. So during MMU errors translation, if valid invalid bit in the page table entry is I, page fall because invalid. AV, so that's mean okay. Okay, so based on this diagram, we have logical memory, page table, physical memory. So page table, when some pages are not in the main memory, so this one is your memory, the computer main memory. Okay, some of the data are not being stored here. Okay. Valid data at frame 4, here is A, 0 for A. Okay, another valid 6 from 2 to C, to 6. And then we have another part is 9. Okay, 9, 5, equal to F. So here is F. So when you look back at this diagram, we have A, B, C, D until H, but only in the physical part A, C, and F. So some page is valid and some others are invalid. Okay, next is about the page fall. So if there is a reference to a page, first reference to that page will trap to the operating system that we call as page fault. So operating system look at another table to decide, and the invalid reference will abort and just not in the memory. And then find free frame, swap the page into a frame where the schedule this operation, and then reset the table to indicate the page now in memory set validation bit is equal to V, and restart the instruction that caused the page fall. This one is about on how to handle the page fall. So step of handling the page fall. Okay, number 1 is refer to the reference. Okay, load memory. Okay, from the memory, load the reference here, and then trap to the operating system. Number 2, trap. Number 3, page is on back install. So here, and then number 4, bring in missing page to the physical memory, and then free the frame. So here now available. Reset page table back, reset here, and restart the instruction again. So these are the steps in handling the page fall. Next is about the demand paging. So aspect of demand paging, we have the extreme case where the start process with no pages in the memory. So that is the extreme case. The operating system set instruction pointer to the first instruction of process, and non-memory resident goes to the page fall. Okay, if there is no memory resident, then we decide as the page fall. And for every other process, pages on the first access, and pure demand paging. So actually, a given instruction could access multiple pages and multiple page fall. Consider the fetch and decodes of instruction with adds 2 numbers from the memory and store result back to memory. So pen decrease because of locality reference and hardware support needed for demand paging. So page table with the valid and invalid bits. Okay, valid is V, invalid is I. And secondary memory, swap device with the swap space. Instruction, restart. So this one is about the aspect regarding the demand of the paging. So in restart instruction, consider an instruction that could access several different locations. Okay, we have the block move. So here is the block move. So auto increment and decrement the location and restart the whole operation. What if the source and destination overlap? What happened? Okay, you can try to search on when we do the restart for the whole operations. What if the source and destination overlap each other? Okay, next is about the performance of demand paging. Stages in demand paging is the worst case scenario. Number 1, trap to the operating system. Second, save the user register and process state. Number 3, determine the interrupt was a page fall. Number 4, check what is the page reference, either is legal, and determine the location of the page on the disk. Number 5, issue a read from the disk to free frame. Okay, you can refer back from the previous diagram. We have the free frame 6 step. Okay, in order to identify the page fall. Okay, so based on that one, wait in a queue for this device until the read request is serviced. Second, wait for the device or seek latency time. This one. Number 3, begins the transfer to the page for a free frame. In this one, if we have issue a read from the disk to a free frame. Okay, then we continue number 6. While waiting, allocate a CPU to some other user. So we can utilize the CPU. Number 7, receive an interrupt from the disk input-output subsystem. Number 8, save the registers and process state for the other user, and then determine that the interrupt was from the disk. Number 10, correct the page table and other tables to show that page is now in the memory. Number 11, wait for the CPU to be allocated to this process again. And number 12, restore the user register, the process start, the new page table, and then resume the interrupted instruction. So these are the stages in the demand paging with the worst case scenario. Okay, 3 major activities. We have the service the interrupt, read the page, restart the process. So service the interrupt, careful coding means just several hundreds instruction needed, while read and page means a lot of time. Okay, restart the process, again just a small amount of time. So page fall rate is 0, lesser than P, and P is lesser or equal to 1. If P equal to 0, no page fall. And if P equal to 1, every reference is a fall. So the effective access time, EAT. EAT here is referred to effective access time, not estimation arrival time. Okay. So 1 minus P and then times the memory access plus P refer to the page fall overhead plus swap page out in swap page in. So example here, memory key access time is equal to 200 nanosecond. Average page fall service time is 8 millisecond. So you see here, we have different measurement. One is in nanosecond, another one in the millisecond. So EAT 1 minus P times 200 plus P 8 millisecond. So 200 here, 1 minus P times 200 nanosecond plus 8 millisecond. So you need to convert 8 milli to the same measurement, nanosecond. So here you will get this value. If one access out of 1000 key causes a page fall, then EAT is equal to 8.2 microsecond. So this is slowed down by a factor of 40. So if we want the performance degradation lesser than 10%, so 220 is bigger than 200 plus 79999 800 plus 5P. So you will get a P lesser than 0.00000025. And less one page fall in every 400 memory accesses. So that is the possibility. Okay, here is demand paging optimization. So swap space input and output faster than the file system input and output, even if on the same device. Swap will allocate in larger chunk and less management needed than the file system. It will copy entire process image to the swap space at the process load time, and then the page in and out of the swap space. Okay, we'll use in all the BSD, Unix or operating system. Demand page in from program binary on this, but discard rather than the paging out when the freeing frame. And then use in Solaris and current BSD Unix, and still need to write to the swap space. Pages not associated with a file. Pages modified in the memory but not yet written back to the file system. For the mobile system, typically don't support the swapping, and instead of swapping, demand page from file system and reclaim read only pages. Okay, next part is about the copy on write. Copy on write. So we have the term COW. So this copy on write allow the both parent and children processes to initially share the same pages in the memory. So either the process modify or share the page, only then in the page copy. So copy on write or COW is allow more efficient process creation as only modified pages are copied. And in general, free pages are allocated from a pool of 0 fill on demand pages, and full and pool should always have free frame for the last demand page execution. You don't want to have a free frame as well as other processing on the page full, and with 0 page before close allocating it. And why 0 out of page before allocating it? Okay, you can try to think why the 0 out of a page before we allocate this part. Okay, for the vfork function, okay, function vfork variation on the fork, system call has parent suspend and child using a copy on write address space of the parents, and designed to have children call execute or exec the bracket very efficient. So this is before the process 1 modify the page C. Okay, process 1, and we have the process 2, and then here we have the physical memory, page A, page 2, and page 3. Okay, when there is no frame, okay, used up by the process pages and also in demand from the kernel input output buffers and extra, and how much to allocate to each. Page replacement here, find some page in memory but not really in use and page it out. Algorithm ultimate, swap out, replace the page, and then okay, and then after replace the page, the performance, okay, based on the performance depends on the algorithm that we use. So an algorithm which will result in minimum number of page fall. So in order to identify the performance, we need to look back on the algorithm, and some page may be brought into memory several times. Okay, so that's all for the first part of virtual memory. Okay, later on we continue on next video with the visual memory. Thank you and Assalamualaikum.